volts to 1 volt, 50 to 1 step down in the converter, and what is that going to be? 0.02, 0.2, 2% duty ratio. Okay? And still you are the 2 megahertz frequency, but it's okay because you can turn on and off in 10 nanoseconds and so on. Well, you're forgetting one thing. Look at a diode in a MOSFET, a diode in a buck converter. If it is 50 volt input and you have 1 volt output, that synchronous rectifier MOSFET or a diode there sees 50 volts. Actually, because it has hard switching, there is no soft switching on a buck, you have, with the spikes you have to, and margin, you have to use 100 volt devices. And you're delivering what? You're delivering 100 amps. So that carries the full power, that MOSFET carries full power at 90%, 98% of duty ratio carries the 100 amps of a current. So all the power is in that MOSFET, and you're delivering 1 volt, 100 amps. You're delivering 100 watts, and you're using 10 kilowatt converter. I call that overkill factor of 100, right? And these people who are making gallium nitride as a devices, they talk about figure of merit, how great is the figure of merit of gallium nitride versus the silicon, etc. I agree 100% with it, and I even know better way to use gallium nitride than they do. But the problem is nobody talks about the figure of merit for converters. Is this a good figure of merit that you're 100 times overkilling in the power? And I had explained it to one of the companies. There are 330 companies in the US and all making synchronous rectifier buck, about $10 billion business. And one of them, I talked to them, I won't tell the CEO or CTO of that company, I said, Dr. Chuk, but we are not taking the 10 kilowatt for that. She says, of course not, but you're buying a switch which is capable of 10 kilowatt and using it for 100 watt, right? Okay, so that's another point. So tremendous overkill factor. The voltage is 100 volts instead of 2 volts compared to another converter. The current is 100 amp, and that's another point. How do you switching that current with that inductor? That inductor is not only bad because of air gap, but it's bad because it looks like a current source, and when you have a current source, what happens? You have turning on and 100 amps and turning off in 100 amps. How good is that? Layout at 2 megahertz, all the talk about it. I don't need that. What about if my synchronous rectifier diode, as I showed on the right-hand side, it has a half sine wave. Starts at 0, goes to peak, and it comes down to 0. You're turning on a diode at 0 current and turning it off at 0 current. And only when the diode knows that it is switching is in between. But at the moment, instance of switching doesn't even know that it's going to be a switch. You know what I'm saying? So layout and all the problems notwithstanding. And a voltage is 2 volts. I have a configuration when the voltage is equal to the output voltage. In this case, at 50%. And of course, I operate at 50% duty ratio in this converter, which is actually take on tap inductor, but it is not because it has 3 switches. And therefore, it has capacitor in series, and that allows circulating current. That capacitor in series, by the way, is also protection. You know what happens when main top switch gets shorted, if it fails short? Well, you're using 10 watt VRM regulator to drive the $800 microprocessor, and you're killing the microprocessor because suddenly we're going to see 12 volt instead of 1 volt. In this case, the capacitor in series is automatic protection because the capacitor in series and the output capacitor follow the capacitive divider, and that is actually can be designed so that even if the input switch fails short and it's turned on, well, the output will see just ratio of the 2 capacitance, which is 1 volt or less, okay? But anyway, these are side issues. So the point is, this configuration, not only these are problems with the buck, and these are no problems with the, what I call a Chuk Buck 2. I kind of came up with that name because originally I have another converter, isolate converter, which is I call a Chuk Buck, and then I need to give it a different name. So have you ever heard for a city called Timbuktu? It turned out it was actually capital of Mali, all right? But anyway, so what I'm coming, this is my conclusion after 40 years in this field, okay? I wish I came up with this, 20 years ago, but maybe the industry will be still even more responsive to it. But what's happened? I'm looking at left-hand side, buck converter, legacy. And PWM and all resonant and quasi-resonant methods that you're using on it, it looks like an inverted building. It's sitting on a buck converter at the bottom and has a next layer of flyback and forward. Above that is a phase-shifted full bridge and phase-shifted full bridge. Then you have a resonant type of converters and LLC converter, which I always consider like whoever really proposed to kill the beautiful transformer in a full bridge and make out of it LLC converter, which instead of having 1% magnetizing current has a 200%, twice as high as input and output current. That's not a transformer. That's a misnomer, you know. Okay. Anyway, so on the right-hand side, you see what I showed here. On the right-hand side is new system. What we need now is not just new topologies. Even layer before that is a new switching methods, but not the resonant that we are using now, which allows the current to go through zero and goes through several cycles, and then you have problems how to control it, switching frequency changing relative to resonant frequency, and so on. No, my three methods that I utilize, they're all, of course, they're all capable of changing the, regulating output, changing the frequency with respect to resonant frequency. But more important, I can use a constant switching frequency, design resonance when I wanted to, and change the output voltage and regulate with a duty ratio change. And there are three methods. One is what I call it hybrid switching. One switching interval on time, say, is like PWM. Off time is just a half resonant, half sinusoidal resonant. The other method is what I call storageless, because it has two resonances. It doesn't store anything. And then the third method is optimum, which is a little bit ahead of what I'm ready to talk this time. Next layer is a non-isolated converters, which now have two resonant inductances. And these resonant inductances are 100 times smaller than your PWM inductor. And what happens? I can use actually for these resonant inductances at 50 kilohertz, I can use it one turn. I don't even have to make coil with the 10 turns. One turn, all I need is 25 to 50 nanohenry inductance, which I can get for a single turn, you know, a piece of wire. And two resonant inductance like that give me the basically very large step down, eliminate switching losses, you know, beats a buck, you know, anytime. And provides a large step down if you wanted to. All right, so now here is a forward and full bridge converters. I just mentioned the problems, and you'll find out that, you know, for example, forward. Output switches, diode on output side has to be 3 or 4 times higher voltage rating than the DC voltage that they are outputting. On input, the same thing. Input switches have to be 2 or 3. Why? Because that so-called, on a buck converter, you have this voltage clamp. Voltage clamp is really like having a secondary flyback converter on which you don't draw any load. So basically, it uses, forward converter uses a flyback reset. And with that has all the problems of the flyback, okay? So that's why you have a high voltage rating of switches on input, high on the output. But what we really want, we want to have a switches on the primary to have no higher voltage rating than input voltage under any condition. And the same thing for the output. And it's possible, and I have it. But I'm not going to talk today about it. Okay, what is this other one? The other one is full bridge converter, again, shown here. And now, let me go. One thing that when I came up with this converter, everybody was shooting at my converter and said, oh, it's bad because it has a capacitor. In fact, many people said it won't work because capacitor is in series with the input. So how could the DC on input transfer to the output? Well, capacitor there is not in series. It is as a circuit with the switches, looks like it's series, but when you take into account switching, the diode, when it is turned on, capacitance is charging, so it is actually in parallel because the left-hand side of capacitor, right-hand side of capacitor grounded. When you turn the main switch on, then the voltage on a capacitor turns off the diode, and now you have positive side grounded, so it's always in parallel, you know. So, and it has only 2 switches. Now, what I looked at that is, if you see here, this is a configuration with the isolation transformer. This is the only converter which has a single-ended configuration of a transformer. Because what it takes, just split this capacitor into two in series and throw in 1-to-1 turns ratio transformer. So basically it operates, isolated or non-isolated, operates just the same way. What happens with a full bridge? To make a full bridge out of the buck, to put a transformer, you need 4 switches. It changes operation. To regulate it, you need a dead time and all kinds of problems. So now I put this isolation transformer, and that's an isolated version. Now, 40 years anniversary was, April 1st, 1975. I was in a hospital having a surgery on my knee. That's why I'm crippled now. So they took my meniscus. And that's when I came up with a converter. I had nothing to do for 3 days. So couple inductors, integramagnetics came shortly afterwards. I'm really happy to report that my new switching methods and my new converters, they all can utilize full advantage of a couple inductors integramagnetics. That's number one. And number two, the state space averaging, which I invented and introduced to this field 40 years ago, 40 plus, right, in 1975. State space averaging equally applies to this hybrid switching and storageless switching. It doesn't apply to all these quasi-resonant, resonant, and LLC converter, but because they are deficient anyway. Blue. Let us now examine in closer details what are the parameters responsible for the saturation in the switching converters and in the magnetic devices in general. First, if we excite a core with a square wave voltage with identical positive volt seconds and negative volt seconds, we will excite the core flux linkages in one direction, shown in red, and de-excite it with the same amount, and therefore in a steady state we will have the periodic excitation up and down along this linear part of the curve. If we are still in a linear part of the curve, we will have corresponding current to be of the same linear shape. Let us now look at what is the main equation. As we see here, the volts per turn that the single device, magnetic device, can support has to be less than this quantity given here, which is directly proportional to the switching frequency, cross-section area of the core, and the magnetic material flux density. Therefore, from here we clearly see why there is a trend toward reducing the core sizes and increasing the switching frequency in switching converters. For example, by increasing the switching frequency by a factor of 10, say from 10 kilohertz to 100 kilohertz, this immediately allows us to decrease the core cross-section area by a factor of 10 and still maintain the same flux level below the saturation of the core. So this is a primary motivating force to try to increase the switching frequency and reduce the volume and weight of the magnetic devices. Another motivating force is toward a better new magnetic material. In fact, we see instead of the ferrite, which has a 0.4 Tesla flux density, if we use silicon steel or met glass on some other magnetic materials which have 1.6 Tesla, right there we have a factor of 4, which allows us again to reduce the core cross-section area by a factor of 4, therefore to come up with a more compact magnetic design. Of course, we can reduce flux swing by reducing the volts applied to the core or by increasing the number of turns. And we saw that in the previous demonstration, again, just showing here, by reducing the voltage drive, we can essentially reduce the flux excitation in the core and avoid the saturation, just like by increasing, again, switching frequency, we can decrease the flux swing and get out of the nonlinear region.